Probability trees are a powerful way to visualize and calculate what happens when events occur in sequence. Take the following example. A gamer is in a knockout tournament. To reach the next round, they must win at least one of two matches. Each match is independent, and the probability of winning any match is 0.4. What is the probability they qualify for the next round? The information in this question is best organized with a probability tree. This tree will have two layers of branches, one for each match. Every match has two possible outcomes, win or loss. If the probability of winning a match is 0.4, then the probability of losing is 0.6. Then we repeat the same structure for the second match, branching off each outcome in exactly the same way. Because these matches are independent, the probabilities don't change from one match to the next, so each layer of the tree looks the same. On the tree, each branch represents a possible result. To calculate the probability of a particular sequence, say winning both matches, you just follow the branches and multiply the probabilities as you go. Now the question asks, what's the probability the gamer makes it to the next round? To pass, they need to win at least one of the two matches. This is where the probability tree is so useful. It lays out every possible outcome clearly in front of you. At first, you might think you need to add up the probabilities of all the different ways they could win at least once. But that's a lot of work. Instead, this is the perfect moment to use the complement rule. The only way they don't reach the next round is if they lose both matches. So, rather than adding up all the winning cases, we just calculate the probability of losing both and subtract it from 1. That gives the probability of winning at least one. Probability trees aren't just for independent events. They're also perfect for dependent events, like drawing cards from a pack without replacement. So let's say we're at a school fair, and you only win a prize if you can draw 2 red cards in a row without replacement from a pack of 52 cards. We'd set up the probability tree with 2 layers of branches, one for the first draw and one for the second draw. The upward branches will represent red cards, and the downward branches will represent black cards. On the first draw, the probability of picking a red card from a pack of 52 is 26 out of 52. That's the same as 1/2, but we'll keep it as 26 over 52 for clarity. So the probability of picking a black card is also 26 out of 52. Now, if we've already picked a red, the probability of picking another red is 25 out of 51, since one red has already been removed and the total has dropped by 1. On the other branch, if the first card was red, the probability of then picking a black is 26 out of 51, because the number of black cards hasn't changed, but the total is still down to 51. If instead the first card was black, the probability of picking a red on the second draw is 26 out of 51, and the probability of picking another black is 25 out of 51, since one black has been taken out of the pack. Finally, to work out the probability of drawing 2 reds in a row, we simply follow that branch of the tree and multiply the probabilities together. That gives us 25 out of 102, which is around 24.5%. And that wraps up our second example. Probability trees let us handle both independent and dependent events in a clear, systematic way. They don't just give us the answers, they help us see the logic step by step.